important. But of all the areas, we identified at least for a short presentation, the four or five areas which are important. One is the risk analysis, certification of software, which is the heart of the whole AI systems, cyber security, and the human aspect. You may be surprised why I'm bringing human in autonomous. We'll come to that. The risk is fundamental in any design, especially in shipping, whether it is shipping or aircraft, it doesn't matter. The risk is fundamental. What is required to be addressed is, we start with high-level risk. Before when we make a concept design, high-level risk, where it is operating, what functions are getting automated or autonomous, and what is the implication of if the system fails because of system failure, loss of communication, lack of data transfer, whatever. So it addresses communication risk and the risks in the trials. In fact, IMO has come up with a circular MSc 1604, which talks about the risk associated with mass trials. We will come to that slide later about talking about what has to be addressed in those risks. There is a slight difference between the conventional risk analysis, what we do, like a DP, FMEA we do, integrated bid systems. Many ships we do FMEAs and risk analysis. In all those risk analysis, we are basically focusing on the loss of a hardware. A particular hardware is not functioning, what is the implication? Loss of software is also addressed, but there is no decision there. So loss of hardware and the inbuilt software is what is analyzed to see the risk associated. But when you come to autonomous ships, because some of the functions are shared by the human, some by the system. It is totally autonomous, is totally different issue. When we are talking about a gradual in between, some functions are shared by human, some by the system. So how do they coexist when one thing, there's a loss of one function, how the human reacts to it? So that is also risk involved, that's why the human element has been brought into the picture of one of the important focus areas. This MSc Circular 1604, which talks about, there is an interim guidelines on safe conduct of mass trials. IMO requires that safety environment is to be addressed in these trials. Before conducting the trials, the risk has to be analyzed, including the risk due to cyber security, loss of communications, and loss of any systems, critical systems. And of course, we do carry out the risks as part of IRS scope. This is one of the most important aspects of AI, rather autonomous systems. There are few critical areas we need to address. The first and foremost is, depending on autonomous level, we need to analyze and at the conceptual stage, what would be my emergency response? Because things can fail. So we need to understand, yes, if the things fail, what is the response process? How do we respond to a situation? And how the system and the human are sharing the responsibilities. AI, as I said before, is all about data. It starts learning from the data. You show a ship, it recognizes it as a ship. So data plays a very, very important role either in the situational awareness or in transferring the data from the ship to shore. Data is everywhere. So data quality, data sharing becomes very important. And when we talk about AI data, there are three types of data they'll need to call. One is training data, that is like, let us say when a kid starts learning in the early stages, the mother's parents show him an apple, elephant, a bus, so that he keeps on looking at it and learns this is what the object is. That is the first step. That is what we call the training set. Then there will be a development set, which is similar to that with more number of images, so that we validate and test the data is okay or not. The last one, the test data, has to be entirely different from these two. For example, let us take a ship, because we are talking from maritime field. Initially, you show the ships of other ships, a radar image with a clear radar image so that it can recognize the other ships. But when it comes to test data, we may show a night vision radar, a foggy weather, a ship in a foggy weather photographs. The system should be able to recognize it. That is the real life scenario. In real life, you may have a fog, maybe heavy rains, and the radar picture, whatever it captures, that has to be seen and comprehended by the system. So the training data, test data has to be a little bit different from the basic training data. The next part is the algorithm. Algorithm is nothing but code. It looks simple. But while the coding has its own complications, there are a lot of systems, new softwares have been developed to do the coding. But what to code, how the situations are to be coded is a challenge. If that has to be done by a particular domain expert, because he also knows how the situation is and what action has to be taken for a particular situation. So algorithm testing becomes very important. And one point I would like to say here is, even if an AI system is developed today, let us say, it has to be validated at regular intervals to see that there is no drift from what was originally decided the model has to do and what output is giving now after a few years. Let me a small example. Suppose there is an AI system which is developed to find calculate the cost of an apartment in a given area. The cost is the variable factor. The fixed factors could be what is the floor we are looking at, fourth floor, fifth floor rise is there, where it is located, approach to a near railway station, approach to the hospitals, schools, roads. So these are all the constant factors. People from the Bombay, let us give an example, like there's a Ulve place called Ulve, when you go to JNPT. 4 years back, the cost of apartment was 25-30 lakhs we are getting for a 2-bedroom apartment. But as in last 5 years, roads have developed. There is a train coming from Belapur to that JNPT. So the connectivity has increased. In that context, what happens? If the old AI still gives me the same value, it is no longer correct. The situations have changed, then data has changed. Unless the new data is fed in, the AI no longer gives accurate results. So it is called a drift in the data. The model has drifted because the data is no longer updated. So updation of data is very important. Second, of course, this is called a concept. Sometimes the concept itself may change. It is called concept drift. And of course, the selection of data is important, and test cases, and there should be vessel, and test case has to be relevant to the vessel, where we want to operate and type of the vessel which is going to be operated. A small example, let us say you are collision avoidance, one of the important things in autonomous ships. If a normal navigator were trying to check his knowledge, whether he has understood the call rules properly or not, they would show him a situation. How do you apply a rule if you're overtaking a vessel? That is, for example. Now, the same is to be done by system. Then it has to be done in a stepwise. A simple example, but I'm not a navigator, so just pick the easiest examples of what. The example which is called like 13, which talks about overtaking a vessel. The normal navigator would have been asked, how do you overtake the vessel? Either you can go port side or starboard side. And if it's a plain water, there's no other traffic around it, the normal expected is to go to take a port and overtake the vessel. That is the normal conventions. So as a first step, if a software is asked to do that, as a rule-based system, it should follow this, taking a port and overtaking it. But as the things become more complicated, you have more ships, then the situation will change. So first thing is, that's why the software checking has to be done as a slowly it has to migrate. So the verification process will be two processes. The case one, we ask, the software gives an output, only decision, no control. And the second stage, it gives a control when we simulate the situation and we verify it is okay. But it is a very simple thing, very simplified, but in real scenario, it can be having more number of ships, more congested traffic, then the situation totally changes. That's why in our guidelines, what we have published for software autonomous ships, between the level 1 and 2 is similar to what IMO has got, but then we had 3 more steps, 3 more levels, 3, 4, 5, because the way we transfer the controls from to the software is done in a stepped process. The level 3, the software takes a decision. So level 1, it takes a decision and doesn't take a decision, it throws a decision to you. Level 2 is similar. Level 3, the software takes a decision, but the operator has to give an explicit yes before it can proceed further. So it cannot execute by itself. So our confidence in software slightly increases. Otherwise, what happens is just make it autonomous is totally dangerous. So next level is make it gives a support, tells you what it wants to do. The operator accepts it, it does. The next level, it takes a decision, informs the operator, yes, I am going to do in this way. It waits for a predefined time, 10, 15, 20 seconds, whatever time you set. Then it executes the decision. The last one, it is totally by itself. Like what we generally see in a house, in slightly lighter side. A class 5 student, we want to go for playing out. He says, mother, can I go out? The mother says, no, let me look at the homework you have done or not. She looks everything, then guess, go. Fine. Then next, he comes to class 10 or something. He just says, I'm going. He waits for the mother to say, no, he's out. And the last, when he comes to college and all, he's totally independent. So he's not waiting for any answers. So that's how he slowly migrate from normal level to autonomous levels. It is data everywhere, either data flowing inside the ship, data flowing from ship to shore, data residing in the computers in the shore center, or in the ships, or in decision-making process. There's data everywhere, and whenever there's a data, and when it is going through, and a lot of algorithms to make decisions, there is always a risk of cyber. So cyber security becomes a very important aspect to be catered, to be understood and implemented. And risk analysis at the very beginning stage is very important. And while we do the risk analysis, there's a risk of the data also is considered, whether data is in transit or at the stationary, what we call typically data at rest. And normal approaches to has a defense in depth. Defense in depth is nothing but you have a multiple controls, so that even one control fails, still the second control takes care of that. And while we talk about cyber security, the present trend is somehow meet whatever the computer can give, you take the computer thing and rest all try to meet with the procedural controls. We say, okay, I have got a lock and key arrangement, my ship is guarded, all those things. But as the ships become technically more advanced, and we are talking of reducing the manpower, the technical controls becomes more important, not just a procedural control. So the equipment what we are selecting should have the capability to execute or prevent a cyber attack. If you, many of us know, the old PLCs what we see in the ships, the control systems, control panels, they don't have username and passwords. We assume everything is fine, the engine room is locked, no one can enter, it's fine. But they don't have the basic authorization of a software. The system can be accessed by anyone. Password, second engineer, username, second engineer, enter. That is fine. But when we talk about autonomous ships and that technology, every system should have basic things of having authorization, accountability, encryption of data when it transfers from ship to shore. So these are required and they can be provided only when your equipment has the capability. The equipment doesn't have the capability, they can't be provided. So checking at equipment level is important, and we have developed a guidelines which talks about capability of the equipment to prevent the cyber attacks. It has got 4 levels of autonomous security levels. The last one, I think, before I will just wind up 2 minutes. The human element, because why we thought the human is coming in autonomous. Normally, the purpose of automation is to reduce the amount of human effort to do a task. But what has been really observed over the years is, as the automation becomes more and more feasible and accurate, the human who is supervising that becomes more and more relaxed. That is a normal tendency of the humans. So, suddenly, let us say situation, you're driving a vehicle or autonomous vehicle. At some situation you can't handle. It says, boss, I can't do, take over. The human can't take over. So this is a paradox we have seen. As the systems becomes more automated, the humans become more relaxed and they are not in a position to just take over in fraction of a second. So that requires, in fact, you must have read in papers recently, when a couple of pilots and co-pilot took a small nap, they put the aircraft not on autopilot mode. And finally, when the landing station came, they didn't land. And the system went out of the autonomous mode because the landing station approached. There was a chaos, somehow they recorded. So handing over the system from autonomous mode to manual mode is very important, and unless the people are totally trained how to take over, how there's a situation, it becomes a very, very important factor. So there,